Hello, my name is Philip Archuleta, and today I'll be addressing my contributions to the CAM2 Crowdsourcing Research Group, in addition to outlining the project's focus and what subcomponents of the project I am directly working to solve. The problem this team is working on solving is a continuation of work from previous semesters. In the past, it was investigated if a crowdsourcing implementation could be used to identify image dataset biases, and the answer was absolutely. We aim on taking this workflow and making it more robust and efficient. Robust in terms of testing representative samples of the original dataset, and efficient in showing the least amount of data to crowd workers as possible. So why solve this problem? Well, better identification of image dataset biases will yield better removal of these biases, which in turn will yield better image identification algorithm training data. This enhanced image identification algorithm training data will lead to more accurate image identification algorithms, which is the ultimate goal of not this project, but future work. So what specifically have I done to assist in solving this problem? Well, let me explain. My first work on the team involved an individual research paper literature review focused on quality control and crowdsourcing. Our previous quality control efforts involved ensuring quote-unquote spam workers who give irrational data will not be recruited. This paper suggests being redundant in showing the same images to multiple crowd workers, ensuring crowd workers are competent before allowing them to work, and preserving outliers in collected data. This paper has allowed me to contribute quality control related insights throughout the semester. Being a new member to CAM2 this semester, I quickly realized that there was a sharp learning curve to being a fully active member on the team, and that if I wanted to meaningfully contribute, I was going to have to put my own time in into learning some foundational concepts. Within the first few weeks of my membership on the team, I had refreshed on Git, Linux, web services, and machine learning fundamentals. This was accomplished through a combination of YouTube lectures, research papers, and sample Git code. When working on our initial problem statement in early February, comparing crowdsourcing image classification results to that of a machine learning algorithm, we first decided to describe each dataset with a few phrases, allowing us in the future to see if crowdsourcing really does outperform artificial intelligence algorithms. As an example, some images in my description of Coco's people class dataset are shown on the slide. Here, I show the results of my analysis of 4 image databases people class, with those databases being Coco, Kitty, Sun, and VOC. All these results align closely with those of my teammates. As can be seen, in the Coco database, there was a focus of sports, food, a lack of focus centering for people in the image, with people sometimes being far in the background. The Kitty database was almost made up entirely of Google Maps screenshots, which all had the same image resolution. The Sun database comprised elaborate architecture, almost exclusively urban areas, and really seemed like images a tourist would take. The VOC database centered people in the middle of most images, with babies, kids, and horses being the highlight. Most images seem posed rather than candid. Next, given the descriptions of each database as previously shown, I participated in a team experiment where I manually sorted 400 images into what I thought were the correct databases, with the goal being to prove that crowdsourcing could actually outperform an SVM machine learning algorithm. The results of this experiment were lackluster to say the least, and ultimately contributed to the team's problem focus shifting to its current topic. Crowd workers were determined to be not good at classifying images by dataset, even when the characteristics and biases of each dataset were known. As can be seen from comparing my results to Ani's, crowd workers tend to have a large variance in accuracy, meaning there was no definitive way to say that the crowd could outperform an SVM image sorting algorithm. With the problem focus needing change due to the results of the manual classification experiment, there was about a week gray period where individual tasks were either vague or non-existent. As such, Haobo created the Django tutorial for the new members and helped me follow this tutorial in addition to setting up a Linux subsystem on my PC. At this point, it seemed like my future focus on the project was going to lie in the front end of the website, but this ended up changing later on. Nonetheless, should I ever need to access the code powering the website, I am now aware of how to do so. Additionally, this Linux subsystem proved useful for the development of Python code later in the semester. Previously, the team had considered using visual question answering to replace step 2 in the workflow, automating the process of having other crowd workers come in and answer the questions created by crowd workers in step 1, where they first describe any potential biases in the given images. This was shown to have accuracy errors, and although an automated alternative would certainly speed up the process and reduce the overall monetary cost, the accuracy loss as an opportunity cost was simply not worth it. To again attempt to automate this process, Ani and I investigated clustering by composition, with the goal being to take images with similar step 1 questions and answers and use this algorithm to see if those images actually have elements in common. Clustering by composition compares pieces of one image with others to see if they are composable, as shown in the slide. Pros of this method were that it was thorough, explainable, and more accurate than visual question answering. Cons involved clustering non-biased similarities and false flags, and upon further review, this method was not adopted by the team. When launching our website for the Cam2 Zoom celebration party, I made a point of quality control testing the web application and ensuring no technical or logistical issues would arise. In step 2 of our workflow, answer collection of the questions provided by crowd workers in step 1, I noticed that if a user was to click the instructions tab, there was no prompt to close it without refreshing the page. I immediately communicated my findings back to the front-end website team, and fortunately this issue was able to be resolved prior to the website's launch. Rigorous testing revealed no further errors, and a lack of error reporting from the Cam2 celebration suggests no errors were missed. Downsampling a large image dataset, or reducing some large dataset of N images to a smaller dataset of Y images, is a core component of improving the robustness and efficiency of our workflow. The team initially tried hierarchical clustering and k-meteoroid clustering for this purpose, but found both of the well-established algorithms to yield sporadic data. As such, Esteban and I looked into unconventional methods of downsampling, and created a new methodology utilizing two simple image description algorithms. First, all N images of the original dataset would be passed through an edge sampling method, as shown by the picture of the dog on the slide. Our research indicated that this algorithm was better suited for small biases in terms of overall pixel percentage, given that this algorithm has little noise and is observing shapes of any size. Images with similar edges would be clustered together, creating some X amount of clusters. Then, each cluster would be passed into a free channel mean RGB algorithm, as shown on the right side of the slide. Given that this algorithm is identifying mean color values between the red, green, and blue channels, our research told us that this algorithm's strength lied in large biases in terms of overall pixel percentage, given that noise would be present along object edges and small objects would not be easily identifiable. The free channel mean RGB algorithm would reduce each cluster to its three most similar images per RGB values, pulling a similar image from another cluster if the given one contained less than 3 images. Given that these algorithms have pros opposite of one another, we thought that this coupling would provide accurate and precise image data. Initial testing was discouraging though, and although a two-step downsampling algorithm was eventually implemented, it did not make use of the free channel mean RGB values or edge features. Following the creation of Esteban's and I's workflow, I developed a Python program to downsample a singular cluster to its three most structurally similar images. I was initially planning on using the RGB free channel mean values for this purpose, but after our preliminary testing, I opted for a different method instead. I utilized Skimage's structural similarity index, which takes into account contrast, RGB values, saturation, noise, edges, and many other features. This is a well-proven, already existing method of comparing images, so I felt confident in its implementation. As a secondary method, if two images had the same structural similarity index, the mean squared error of both images compared to one another would be used instead. Testing showed promising results, but it truly is subjective which given images one considers to be the quote most similar. I have left an example case in the Philip_tree branch on GitHub showing this method in use. Given that Skimage's method is extremely comprehensive and well established, I considered the algorithm working after 6 different successful test cases. As one of my final tasks in the semester, I assisted in a literature review investigating clustering iconic images and brute force feature matching. Neither of these methods have been previously investigated by the team. Iconic image clustering refers to images that are perfect examples, or images that you would use to teach a small child. This is performed through a cross-validation of inputted images with those on free online databases like Google Images. Brute force matching, on the other hand, takes a descriptor feature of some initial image and compares it to all features of all other images, calculating some distance to cluster from. The brute force process has a very high time complexity, but is extremely accurate and is likely to be implemented in the future. Focusing more on the documentation side of the project, I spearheaded the team's submission for the undergraduate research conference at Purdue University. Esteban and I worked on updating the abstract from previous semesters, and then individually I updated the team's poster from last semester and recorded the narration. Given that this year was a little peculiar, the poster had to undergo some significant changes to account for an increased font size and an online format. Any questions can be forwarded to my email listed on the slide or can just be asked through Slack. Thank you so much, Dr. Liu, for the opportunity to contribute to this team. Camp 2 is what I am most proud of since I've attended Purdue, and I absolutely intend to continue on with the program.